So now we move on to our next topic, which is called the memory hierarchy. And in doing so, we will look at the storage technologies to have an idea why it's important. Okay, so we'll look at the storage technology and trends, the cultural reference, and then the caching in the memory hierarchy. Okay. So we all know basically what a random access memory is. That's actually the read-write memory, right? Read-write memory. Okay. And the RAM is basically it's it has it's packaged as a chip. Okay, these modules, and its basic storage is a cell which stores 1 bit per cell. Okay, and we usually have multiple RAM uh, chips to form a memory. Now, when we talk about RAM, there are actually two main technologies, like the static RAM and the dynamic RAM. Static RAM is what you're seeing with these flip-flops in logic design. In this case, each cell, okay, which stores a bit, is implemented in the 6 transistor circuit. Okay, and you remember basically the from logic design that once you save a value, it can retain its value as long as you have power on. It doesn't switch that. And it is, since it basically has this loop like positive feedback loop in its basically design, it's relatively insensitive to disturbances such as electrical noise. It's not, it will keep its storage all the time, but it is faster and more expensive than what's called DRAM. Now, what's DRAM? It's called dynamic RAM, and in this case, each cell is much cheaper. Okay, it's implemented with a capacitor and a transistor. Okay, so you have very little silicon uh, real estate that to use, but its value needs to be refreshed every 100 to 10 to 100 milliseconds. So this is, it's because it's very sensitive to disturbances, and when you actually read from a dynamic RAM, it is basically the value that are stored is actually becomes vague. So eventually it will lose its what it would forget what it was stored. But it's slower. It's slower, but it's much cheaper. So this is basically the RAM is what you have in your computer memory. You talk about 4 GB of memory, etc. You talk about the DRAM technology there. So what we will do is, I will just briefly tell you about the DRAM cell and why is it so important and what it needs for us. So the DRAM cell is essentially very simple. We have a MOS transistor, which you can see it in here, okay, and we have a capacitor, okay, which is grounded. Then we have this gate. Now, like this capacitor, then you can save charges in here. For example, if you want to store one in a DRAM cell, what you have to do is you basically fill this up. Like you have these electrons and in here, so you can then fill this capacitor here. And if this gate is closed here, okay, then this charge will remain here. There will be some leakage though, because in time you will have some leakage, so it cannot retain it because it's just a capacitor, right? And when you want to read it, and you read it by accessing to here. Okay, if I want to, for example, read what this value is, remember this is then what you do is you basically from this gate you open this, okay, and as a result, you can have this currents flowing in this way, okay, and then you can read that it's actually a 1. But once you read it, know that you have now less charge in your capacitor. Okay? So it means that by reading the content of a memory cell actually destructs its content. Okay, because it's such a basically everything is stored on a capacitor. Okay. Now, when we look at this, like the memory, and then what we have is a grid like this. Okay, so you can see these memory elements that basically aligned like this. So we have this, it's called the word line. It means that if I'm storing, for example, in here, you can see that I can store byte, like a byte here, okay, by having 8 of them, so you can read them in here. And then here we have the bit lines, okay, and here we have these connections in here. Now, how it works is when we are basically want to read things, then you activate basically, for example, imagine that I want to read, for example, from this particular line. And here you can see that I have, like, the way I stored 0 here, there's no charge. I have a 1 here, it's charged. I have a 0 here, I have a 1 here, okay? You can say, so this is the initial value, say that on my DRAM. Now, if I want to read, say, this particular word, this one, what I need to do is, you first you basically take these bit lines all to high, okay, to high value, and in this particular case, it can be, let's say that around 1.5 volts, okay. And then you also take this particular word line. This is like, if I want to read this one, then I basically set this to high. Okay. So when you set this to high, okay, then this gate now is open. Okay. For this one, this is not high, so this is low. So this means that there's no leakage. So it doesn't basically set this value. So this is like as if these are disconnected. And as a result, since I have these values like this, and it's set, then the currents that were set here, then since this was 0 here, and this is like the value that I had here was set around, say, 1.5 volts here, okay? Since it was 0, and I had charged it, so the value that the charges would go here a bit, okay? And as a result, the value that I get here is 1.5 volt minus some delta value, okay? A little bit different, okay? Whereas for this one, for the second line, in this case, I had a 1 here, so the charges, when I basically open this gate up, now the charges will then go here, and it would make my voltage 1.5 plus delta some volt, okay, and so on, okay. So as a result in here, then I will have then I have an amplifier here, okay, which will check this against, say, 1.5, and as a result, then you will read this as 0, you will read this as 1, you will read this as 0, you will read this as 1, okay, and after this, then if I want to basically now recharge these values, then you need to again set this to the same thing, and then you want to then write it back into the value here. Okay, so that's called the refreshing code. So with the DRAM cell, okay, you can store a single binary digit. It's implemented using just a transistor and a capacitor. So it's easy to miniaturize and cheap to manufacture. And many cells are connected to word lines and bit lines in a rectangular way. And destructive read means when a cell is read, then you have to rewrite it, okay, because you have, like leaked some voltage in here. And as a result, the charge leakage continues that all cells needs to be refreshed, hence the term dynamic DRAM, okay? Now, to summarize this, of course, like this is just to get an idea of how it's working. For example, for static RAM, okay, which is actually what we have in our registers. Okay, we have the transistors. It is 6. Access time is if it's 1 times x, and it's persistent, meaning that it will retain its value as long as its power is on. It's not sensitive, okay. But the cost is 100 times of a DRAM. Okay, DRAM is much cheaper. Its access time is much slower because you have to wait for that. It's not persistent. It will lose its value. Is it sensitive? Yes, but its cost is maybe 100 times less, and this is what we use in our main memories. Whereas the static RAM, we use them in cache memories, which we will start discussing on Thursday. Okay. So in the conventional DRAM organization, the bits that we have, like if I have a D times V, which is V is the vertices and D the number of elements here, then they are organized as D supercells of size W bits. Okay, and here is for example 16 by 8, so D is 16 and W is 8, DRAM chip. And what we do is here we have this address that's spent here, and then here's the data that's coming out. It's 8 bits because the W is 8. And in this case, you want to access, say, this particular, say, supercell here, supercell 2.1. And what you do is if there are, like you, from the address side, you have you get sent two things. One is row access probe, okay? It selects basically the row 2, which is here, okay? You select this by setting RAS to 2. And then this one is copied into the internal row buffer, okay? And after that, then we have this column access probe, CAS, which we set this to 1. And with this, then we take this one from the internal row buffer and then feed this as the data. Okay, so this is basically how the DRAM accesses work. And what we do is when we have multiple, like in constructing memory modules, for example, each of them may contain just say eight bits here. Okay, so you can have then 8 DRAM modules, and from these then you can essentially read and get this whole 64-bit here in one batch. Okay, so with DRAMs there are a lot of different technologies, and this is just some ideas that we will have here. And here we have some discussions. Again, I have some YouTube-based links which you can go ahead and, if you're interested, and learn more about them. Okay, here we have, for example, this fast page mode DRAM, and this is, for example, accessing the concept of rope with RES, CAS instead of like these. Okay, and we have extended data out DRAM. Okay, which has enhanced fast page mode with more closely. This one is interesting. It's synchronous DRAM. In this case, the clock signal of the DRAM, okay, is driven by the rising clock edge instead of some asynchronous control signals. Then we have DDRAM, DDR. This is double data rate synchronous DRAM, and this is interesting because it's you can basically it uses the STRAM because both clock cycles, so we can have a read here or write here at both edges, like you can do it at the rising edge or at the basically rising and decreasing edge. Okay, and we have DDRAM, etc. So I'm not going to go into here. And then we have, of course, ROMs. I'll skip this, like these different ROMs. These are just read-only memories. So then the ROMs, basically, even the power is off, it can still retain its memory. And we have different types of ROMs: programmable ROM, erasable programmable ROM, and then electrically erasable. This is the most common thing, which is when you have a different setup, you can electrically erase ROM or your flash memory that you have in your US sticks and etc. Typically, the firmware on your computer, the BIOS and other things, they are stored in a ROM. Okay, and so that means that when you're booting things up, you have a code that always resides in there.